very happy to give my presentation about the Wang model for the large eddy simulation of aeolian saltating particle flow. Okay. This is the outline of my presentation. In the background part, I will introduce the phenomena of aeolian saltating particle flow and about the simulation method for Reynolds number multiphase flow. I think many people, all of the audience know that this background, and I will introduce two recent work. The first work is the well-resolved large eddy simulation of the aeolian sand flow. This is for the discussion about the turbulent modulation by saltating particles. And the second one is the Wang model large eddy simulation. In this part, we will give the derivation of Wang model accounting for particles, and finally we will validate the model. Sorry. We all know that sandstorm are a disaster that occurs in the atmosphere, the barytheric boundary layer. In the past few years, I've been working on the numerical simulation of sand flow. Wind and sand movement exist in the form of aeolian streamers near the surface, which are the large-scale quasi-linear concentration of drifting sand in the low parallel direction, meandering laterally, merging and bifurcating as they move downwind. This is to move we take in the field. You see that the non-uniform distribution of sand particle. If you look at the nearby region, we can find that this two-phase flow is always dominated by the continuous particle bed mass transfer. Particle may particle rolling, sliding on the bed, and saltating near the bed or suspending in the main flow. Such flow are also common in nature. Examples include turbidity current, river, sand, aeolian snowstorm, to name a few. In this talk, we will address the saltating particle flow. It is characterized by a splicing process, that is, saltating particle rebound and eject other particles on the bed. When they reach the bed again due to the gravity's settling, this kind of two-phase flow is controlled by many parameters. The most important parameter is the fraction Reynolds number of atmospheric boundary layer. It is on the order of 1 million. It is extremely high. The others are the particle Reynolds number, and the ratio of the particle diameter to the length scale of turbulence, the volume fraction, the Stokes number, and the Galilean number, and the Zhou number that are related to the gravity force. This is the we call it splicing processes. It means that particle will rebound, eject, and collide with the bed particles. In addition, there are different turbulence structure in the atmospheric boundary layer turbulence. The near wall, like the near wall strikes hairpin vortex in the buffer layer region and the low log layer. The large scale motion in the middle log layer, which contribute significantly to the transport and mass and momentum. Obviously, the aeolian sand streamer is directly related to this turbulence structure, and at the same time, this turbulent structure will be modulated by the sand particle through the particle turbulent interaction. So according to the above introduction, we know that aeolian saltating particle flow contain complex physical processes about the momentum, energy, and the mass exchange among particles, turbulent and the mobile sediment bed. And the flow is controlled by many factors. The simulation of this kind of a flow, multi-phase flow, is very challenging because it requires extremely high resolution to reproduce the main statistics and structures of high-Reynolds number turbulence, and a large computational cost and the storage space to track a huge amount of moving particles. Even though the RANS simulation has been used more than 30 years, we believe that large eddy simulation is better for simulating the observed linear concentration and predict accurately the mass flux of particles. It's very important for the sand dust storm prediction. We all know that the fully resolved large eddy simulation of one wall-bounded turbulent flow require a large amount of grid since it solves the inner layer. Therefore, well-resolved large eddy simulation of particle-laden flow is now limited to low Reynolds number. The highest fraction Reynolds number of large eddy simulation of multi-phase flow is just about 1,000. One model areas try to bypass the inner layer and resolve the energy-containing eddy that are crucial for turbulent transport in the outer layer. The overall cost of wall model areas is dramatically reduced, and therefore wall model areas is a practical necessity to apply areas to high Reynolds number particle-laden flow. In this method, we know that one model is necessary to properly compensate the under-predicted wall stress due to the coarse grid near the wall. Many wall models have been proposed for areas of particle-free wall turbulence. One can refer to the excellent review paper of Bill Miley and Larson for the latest progress. In general, this model can be classified into the wall stress models and the hybrid LES and the hybrid areas RAS model. Here we just focus on the physics-based wall stress model because it is relatively simple and is the most commonly used wall model. Dierdorf and Sherman pioneered the use of equilibrium model in the simulation of wall turbulence. It calculated the wall shear stress in terms of the resolved outlier velocity at the first off-wall grid, and then fit the stress back to the areas as an extra boundary condition to be used at the next time step. It has been successfully applied to wall turbulent flow. This model is restricted to simple self flow since it implies the existence of a log layer in turbulent boundary layer. Since then, the model has been I did skip all. Since then, the original equilibrium model has been modified by considering the inclination of elongated structure in the near-wall region, the pressure gradient, buoyancy, chemistry, turbulent structure in the outlier radiation effect, even non-equilibrium effect. But none of this model accounts for the effect of particles. Consequently, as a result, the existing high Reynolds number multiphase flow are usually simulated by Wang model LES equipped with particle-free equipped with straight one model developed only for particle-free flow, all with no sleep condition, even though the first alpha grid is so large that one model is necessary. Such kind of two-way coupling simulation neither properly include the interaction between particles and the near-wall turbulence into the one model, nor accurately predict turbulence and particle transport. We cannot evaluate its accuracy. You see that the simulation, the first of all grid is very large, even more than several hundred. The objective of my recent study is to develop and validate one model for particle laden flow. To this end, we perform two-way coupled wall resolved LES of multiphase flow at moderate Reynolds number. We're discussing the turbulent modulation by saltating particles. Then the result from the wall resolved LES simulation are taken as standard data. We derive the new wall model accounting for particle effect and finally test the wall model in terms of the standard data. Then let's move to the first work, the wall resolved eddy simulation of aeolian saltating particles. Sorry. And this figure from Balachandra shows the range of applicability of different simulation methods for multiphase flow in terms of particle size and volume fraction. For aeolian sand flow, the Lagrange point particle method is suitable because the high Reynolds number, high volume fraction, and the strong momentum and mass exchange among particles, turbulence, and the mobile sediment bed. We address here that even in one tunnel experiment, the fraction Reynolds number is already several thousand. And usually there are almost 1 million particles per cubic meter of air. So the simulation is very challenging. Turbulence in the atmospheric surface layer is simulated in an open channel. We can see the boundary condition here. And the drag force and the gravity force are considered in the calculation of particle motion. The two phases are coupled through the summing of the drag force in each fluid cell. As mentioned before, the characteristic of saltating particle laden flow on sediment bed is that when the moving particle fall back onto the bed due to gravity, it will rebound or eject other particles. In the point particle simulation, this process is described by the so-called splashing function. We don't resolve the particle bed. Instead, we regard the wall as a reservoir and place all bed particles below the wall. When the distance between the center of the impacting particle and the lower wall is less than half particle diameter, the number of the eject particles and the velocity and the angle of the ejected particle and the rebounded particle are all calculated according to several given probability density function. Here we show the PDF of rebound and ejection particles. Here we show the computational domain and the resolution. The real height of the simulation domain is 30 centimeters. It's like an open wind tunnel. We perform two simulations, one for particle-free fraction Reynolds number of 3700, and one for particle-free Reynolds number of 4200. Although the fraction Reynolds number is not very high, it's already the highest Reynolds number available for the large eddy simulation currently for saltating two-phase flow. The total grid number is almost 300 million. And there are 23 grid points within the vertical range of y plus lower than 100 for showing the inner layer of the wall turbulence. We can see the alternating high and low speed streaks in the simulated flow field. You see the blue and the right counter of the streamwise fluctuating velocity. The number of particle tracked in each time step are 60 million. The cost for each simulation is 500,000 hours. This is a movie. Sorry, wait. I have to. Okay, this is a how to. This is we can see that we can reproduce the non-uniform particle distribution and the streaks of particles. To validate the model and the code, we compare the simulation result of particle free flow with DNS data and the experimental data from previous studies. The areas from the left two figure, we can see that the areas result are collectively consistent with previous DNS and experimental data. The maximum difference between the areas and the DNS is found in the inner peak of the mean square of U fluctuation, which is attributed to the insufficient near wall resolution, but it is inevitable for the large eddy simulation. And the right figure we show the volume, the simulated profile of the particle volume fraction as function of the wall normal height. We see and compare with the wind tunnel experiment at a similar fraction or velocity. The areas can reproduce the wind tunnel measurement in quality of the particle concentration. And this is the instantaneous snapshot of the normalized streamwise fluctuating velocity in the horizontal plane at the two different wall normal height. Yes. The upper two are in the outer layer of wall turbulence, and that is in the middle of the log layer, where the lower two are in the near wall buffer layer. The alternating high and low speed streaks are clearly visible in both inner and outer layer region throughout the simulation domain in the particle laden flow. We see that the streaks in particle laden flow are clearly different from those in particle free flow. It is much clearer for the outer layer counters. We see that the right counters, the area and maybe shorter than that in the particle free cases. In more bounded flow, the special two-point correlation of the velocity fluctuation are usually used to estimate the average length scale of typical structures to obtain the effect of particle on turbulent coherent structure. The streamwise and span-wise two-point correlation of the streamwise fluctuating velocity at different vertical position for the particle free and the particle laden flow calculated and presented here. And the correlation scale extracted from the simulation for the correlation coefficient of 0.2 are shown in the right figure with respect to the vertical height. We see from the left figure that we note here that the solid line, the right and the blue solid line are the length and the width scale for of a turbulent structure in particle free flow, and the dashed line are those for particle laden cases. We see from here in the inner layer. We can say that the length scale and the width scale of turbulent structure is increased, and in the outer layer, the scales are decreased. Why? Then we let's first look at the inner layer turbulent dynamics related to the saltating particles. Here we saw the conditionally sampled flow field at a reference vertical height of y plus of 15. The left figure shows the conditional sampled span-wise turbulent velocity during particle ascending phase. We here so this is ascending phase. And while the right figure is that for the descending phase. Apparently, the range and the strength of the positive and negative span-wise velocity for ascending phase is much larger than that for the descending phase by comparing these two figures, which highlight the importance of the particle ejection and splashing process. This is totally different from typical two-phase flow on smooth wall. The enhancement of turbulence that particle induced during ascending process is more significant than the separation of induced during the descending process. That's the reason why the size of near-wall turbulent structure are increased. We call the mechanism of turbulent modulation as the splashing effect. Then let's say the conditional sampled high concentration particle concentration event. The bottom right figure is the isosurface for particle concentration correlation of RCC 0.2 and colored by the local height. We see a hill-like structure of the mean particle concentration distribution. Recall the animation of the instantaneous particle concentration distribution we saw in previous slides. We can easily associate the saltating particle with the large-scale turbulent structure. The non-uniform saltating particle are like an active roughness element to the outer flow field. Here, active refers to the dynamic process of impact splicing movement of heavy particle near the bed, and also the mobility of the streaky particle distribution. The position of roughness element is constantly changing and cutting off the mean outer layer turbulent structure. The left two figures show the streamwise and vertical turbulent velocity in particle-laden flow conditional sampled during according to high particle concentration. It is clear that there are two regions. The downwind red region is the high speed region, and while the upstream blue region is the low speed region. In the middle, we see the high concentration. Here is a concentration, high particle concentration. On the contrary, the large-scale turbulent structure in particle-free turbulence is an inclined high-speed region. By comparing these two figures, the structure seems to be cut by the saltating particles. The addition of particle reduce. This is the last one for the first part. The addition of particle also reduce the mean streamwise turbulent velocity. The streamwise fluctuating velocity and the Reynolds stress are also reduced in the near region, but the turbulent intensity and the Reynolds stress in the out region are increased. The vertical and the spanwise turbulent intensity are also enhanced throughout the boundary layer. We don't show here. The mean streamwise velocity and the Reynolds stress will be used for the development of the equilibrium model. And then let's move to the next work about the more modularized simulation of this saltating particle flow. Before discussing the one model, we need to first know the mean features of the saltating particle flow. Take the simulation case with Reynolds number of 4200 as an example. We show the mean profiles of particle and the turbulent velocity, the log law indicator, the particle momentum flux, and the turbulent shear stress, and the particle concentration and the mass flux. It is seen that mean velocity of saltating particle is lower than the turbulent velocity. Say the upper line is for the particle-free cases, and this is the particle-laden cases, and this is particle velocity. And the plateau region of the log law indicator exists in both particle and free and particle laden. We say that the particle, but the range, the position and the value of the indicator are different in these two flow particle in these two turbulent flow. And the pink line in this figure is the particle momentum flux. We also call it particle stress. Will decrease with the one normal distance, but the shear stress of turbulence increase with the one normal distance. The sum of these two stress is almost constant within the saltating particle layer. And the particle volume fraction, and the mass flux all follow a negative exponential distribution with regard to the one normal distance. These features are very important for the following discussion. Okay, to develop the particle-involved Wang model, let's start from the momentum balance. The total shear stress in the saltating particle flow is the sum of the turbulent shear stress and the particle stress, since the total momentum flux is the consequence of the both particle and turbulence. According to the Plato reason of the log law indicator, we assume that the effect shear stress is almost constant. Also, we can see the figure from the last slides. Within the saltating, it is the total shear stress is constant within saltating layer for the equilibrium two-phase flow. If the mixing length model is in any case employed to calculate the effective turbulent viscosity, then we have the following expression about the resolved turbulent velocity and at any one normal distance and the wall shear stress. This is tau f y0. Y0 is the roughness height of the sediment bed. So the tau f is the wall shear stress. This formula related the area's streamwise velocity with the wall shear stress implicitly. If the mixing length model is used to calculate the effective turbulent viscosity, then we have the following expression. Note that the effective shear stress used as outside the saltation layer can be calculated from the LES data. And then the only unknown in the formula left is the distribution of particle stress, tau p. In the steady state of particle latent flow, the total momentum flux at any one normal distance y can be calculated using the following formula. In this formula, the downward arrow here, the downward arrow indicates the descending, and the upward arrow indicates the ascending phase of typical parabolic like saltating trajectory. The concentration is defined here, and therefore this expression can be rewritten according to the particle concentration. In the steady state of the particle latent flow, the number of particles leaving and arriving at y must be equal on average for the equilibrium state. Then the ratio of tau p at y to tau p at the back surface is can be written as this. Note all can be expressed as a function of the mass flux. Note that there is three multiplier on the right hand side of the equation are just related to the mean particle velocity. Mean velocity and descending velocity and ascending velocity. In terms of the trajectory analysis in these two papers, we the continuous product of dimensionless particle velocity can be simplified as a linear function of the one normal distance, in which the h H bar is the mean height of saltating trajectory. I don't show the detailed derivation of the formula how under the assumption for this formula. If you are interested in this derivation, you can read these two papers out. My paper published in International Journal Multi-Phase Flow. If we have the expression, then we can obtain the rewrite the this is one model actually. We rewrite the formula as this. The one model holds within the height range of logarithm, and y lower than the mean height of saltating trajectory, and must be solved iteratively because it is an implicit equation. The wall stress tau f in the particle laden flow could be calculated once we know the distribution of particle mass flux qy, the mean particle saltating height h bar, and there is a correction coefficient. The final expression of particle involved one model is shown on the top. Previous study have reported several simple semi-empirical expression for mass flux and the mean height of saltating trajectories. We compare the well-resolved areas result with them and find good agreement. Therefore, this model are used in in the one model here. These two parameters. The parameter gamma can be estimated based on well-resolved LES result also. We first calculate the priori gamma according to the well-resolved LES data. It is 1.26 for case with particle-free Reynolds number of 4,200. After publication of the paper, we derive the value of gamma from one tunnel experiment. It is function of the fraction velocity as shown in the rightmost figure. Moreover, to use this model, there must be more than I think 10 grids in the particle layer to capture the as much particle information as possible, and the first grid point should be in the log layer. The fraction velocity can be calculated based on the LES data from previous time step, and the mean saltating height and the dimensionalized particle mass flux distribution are calculated by the semi-empirical model of this. This is two models used in the wall model. And then we can obtain the value of the wall shear stress by iteratively solving the about equation in terms of the mean LES velocity at current time step and feeding it back to LES for the next time step of LES. Here we present the particle volume fraction and the horizontal mass flux calculated by the traditional wall model, the Pio-Meli model and Young model, and the new developed model. Here the model. All results are compiled with the standard data. We see the blue line is the wall resolved LES data. Note the vertical coordinates. The volume fraction and the mass flux are scaled by the volume fraction and the mass flux obtained from the wall resolved LES at the first off-wall grid point. So if the value of the vertical coordinate is 1, it means that the 1 is the wall resolved areas data, and the value of the vertical coordinates indicates the relative arrows between the wall model areas and the wall resolved areas. We also present here the coarse grid areas. It means that we use the no slip condition for the lower boundary as a lower boundary condition. We say that without one model, the coarse grid LES predict cannot report a maximum relative error of more than 90% of particle concentration and more than 150% of particle mass flux. The error is very big. Although the particle wall model can improve the simulation result, the error reduced to about maybe 70%. It is also very big. The new model we proposed reduce the error to about maybe 30%. It is shown that the results are significantly improved by the new model accounting the particle influence. Also, the computational load has been reduced to maybe 1/6 of wall resolved LES. Okay, let's come to the conclusion. We performed more resolved large simulation of particle latent flow over sediment bed, and this data was used to discuss the turbulent modulation, and also the data was used to be in standard data for the development of the new wall model accounting for the influence of saltating particles. The result finally we validate the wall model areas, and we found according to the standard data. But we know that the work was not has not been finished. How sensitive the model to the assumption is to be studied, and the model needs to be calibrated in the future based on maybe experimental observation or high precision numerical simulation at sufficiently high Reynolds number. The model we proposed is based on the mean velocity and the mean wall shear stress, and the prediction of fluctuating wall stress is ongoing. Thank you for your attention. And the work I show here could be found in this two published paper. And here the picture is the observation station our group established in desert. This is we call it QLOA. It is observation station for the high Reynolds number turbulence and sand and dust storm. The main tower is maybe I think is 32 meters high. So many instruments was installed on the tower. So if you are interested in the measurement result, maybe in the future we can invite my colleagues who do the experiment measurement to show their show his result. Thank you for your attention.
Thank you very much, Professor Wang Ping, for an excellent presentation. Very interesting topic and impressive work. So there is now time for some questions. Maybe we can start. I think there's a question about particle collisions and the concentration near the wall. I think there was a picture on slide 26.
Okay. Okay.
I think there was a picture of some field in the flow, and you could also see some particles.
Yeah, I saw the question.
So in the picture on slide 26, I think you could see that there's a bed of particles, and if I remember,
26.
Yeah.
26.
Yes. So in this picture, I think so this picture, so we can see in the top figure, we see, I guess the white circles are particles, right, which are collected close to the bottom of the picture. Is that correct?
Yeah.
So it appears that the particle concentration is high, but I also remembered you talked about the splashing model where some particles were actually outside the boundary. So can you maybe you can say something about that? Is this a really high particle concentration in the flow, or are we seeing something which is outside the domain of the LES?
That's a good question. When you enlarge the particle, actually the particle in the boundary layer is very small, and the probability, yeah, even though the sorry, is there any concentration profile? I don't remember.
Yeah, okay. There was. Okay. I don't remember what's. Okay. Yeah, that one maybe.
This is a profile of the concentration. Actually, it's not very high. In our simulation, it's not very high. You see the vertical coordinates. And in this slide, the particle size was enlarged. It seems to be very large.
Yeah, I see. So that we can see them, but they are actually much smaller. So it's the visualization.
Yeah.
Okay, so then you don't need to account for particle collisions in the boundary layer. But then the feedback effect.
I think, actually, we calculate the probability of the particle collision is very maybe lower than 1%. 1%.
Yeah.
Because it is impossible for our simulation for us to consider the particle collision in the simulation, because you know that the number of particles we track in the simulation is more than 60 million.
Yeah. Yeah, I fully realize why you do not want to check for collisions or resolve collisions. Yeah. So the feedback effect from the particles on the fluid is that via a source term. Then there is no volume fraction, right, in the the balance equations for the fluid. So the way that the particles influence the fluid is from the momentum exchange.
Yeah.
Yeah.
Here.
Yes. Yeah. Okay. And let me see. So yes. So on slide 23, there were those active roughness elements that were very interesting. So how should we understand this physically? Is it that to the outer flow this looks like a rough surface, or what is the interpretation?
Yeah. Okay. This is a very good question. Actually, the particle bite is itself a roughness bite. And when the two-phase flow forms, we see maybe the movie here.
Yeah.
Here is a simulated particle distribution. We see that the particle strikes always meandering, and when they flow downstream, and we see the high particle concentration with and many blank area, many and they will changing continuously changing the particle distribution, particle concentration distribute always change, and on average, in this slide, we see that particle concentration is not uniform in the vertical direction. It's like a hill. So the hill here and there, and almost change his position. And in this at the same time, we see many different the hill like particle high concentration events. And we think this is the active roughness element.
I see. So I assume that in these simulations, so the lower the wall is flat and the particles are spherical. So I guess in reality you will have a roughness even if you do consider like a lower boundary that does not which is steady and does not emit any particles. It will not be flat, and I guess there could be variations in particle structure or morphology or shape. Do you expect that those different properties of particles could have an influence also on the turbulence?
Yeah, I think it should be different. But in our simulation, the particle is sphere.
Yeah.
And yeah, it's sphere.
So and then as you showed also in this very nice last picture, so you want to maybe, let's say, predict sandstorms, emergence of sandstorms and how severe they can be. So what kind of information? I guess that is not an LES, but that is some other kind of reduced order model. So how can the information from this work be used to help predict the appearance of sandstorms?
Yeah, very interesting. I think actually we are working on the improvement of the sandstorm prediction model. Actually, this is the mass flux is a very important parameter for the sand dust prediction in the prediction system. So if we can accurately reproduce the mass flux using maybe LES models, or we can propose some correct prediction model about the mass flux. It will provide the sandstorm prediction system suitable lower boundary condition. I think this is the most. I think that this is this is the perspective of this area simulation.
Yeah. So it is. Thank you very much again for a very interesting presentation. I think we've had two very interesting presentations on atmospheric flows, both close to the ground and high up in the sky, but facing a bit similar challenges in this wide range of scales, very small dispersed entities and large-scale turbulence, and all of the challenges that come with trying to describe this in a way that is effective and that works. And it's really nice to see the ongoing work in these areas and how the research front is consistently being pushed forward. So very nice, and a big thank you to both speakers of today, and to everyone who came and listened to the meeting. John, do you want to say something?
Yes, thank you very much for chairing today's meeting, and thanks Professor Gaetano and Ping Wang. And the two speakers give us a very excellent, actually, their presentation today. And thank all of yours. And Professor Takashi Masayama is also here. Presently, Japan time actually is 10 p.m. Thanks a lot for your attend this meeting today. Yes, see you next month. See you next the meeting. Yeah. And have a good day. Have a good evening and good afternoon. Yeah. See you. Bye-bye.
Bye. See you. Good evening, good night, and good day.
Yeah.
Good.
Thank you. Thank you. Bye.